Hello, everyone. I would like to welcome you all to Introduction to EES for Thermodynamics workshop. My name is Tarifa Bahri. I'm a fourth year student from Mechanical Engineering Department. So this workshop is conducted to help the student to understand the basic of engineering equation solver or EES, specifically in the field of thermodynamics. So what is EES or EASE? EES stands for Engineering Equation Solver. It's a software capable of solving hundreds of linear, nonlinear, algebraic, and differential equations. It has a built-in function for thermodynamics and transport properties of many substances. That means EES stores thermodynamics properties, and by using a code that calls these properties, instead of solving the problem by hand or using the table of properties that usually in the textbook and takes a lot of time. Also, you can generate PV, TS, and other plots and do analysis for you. So without further ado, let's get started and explore the EES. So to start the program, you can do File and Open, and then a window called Equation window will appear to you. At the bottom of it, there's different parameters, but most importantly, these parameters. So when you click on it, it shows you that you can change the units to SI units or English units, and for the pressure units, temperature, energy. Let's get started with the basics. How you can write the operation, run it. Basic one is the addition. So 2, let's say, name a variable called A equal 2 plus 2 minus 1. And for the multiplication and division, A underscore 1, I'll tell you what's the meaning behind the underscore, equal 5 times 5. For the multiplication sign, you're going to say type the star, and for the division, /5. And for the exponentiation, let's say another variable, A underscore 3 equal 5, and then you type this sign, it's called cetera, or I think it's called cetera, which means squared 2. Now, first, basically, we check the equation that by pressing this this box, or by going to calculate check format. So we're going to check. We have 3 equations, 3 variables, no errors were detected. And then you are going to press this box, or we're going to go to calculate solve. And here it is. So as you can see, when I typed A underscore 1, that means A subscript 1. So that's for the simple operations. But this window is like a calculator for you. And now, if you would like to write a comment, usually you would type a quotation. Let me just read this. Quotation, then first example, and end it with another quotation. Or another way, you're going to type the curly brackets, second, and then close it, or another curly brackets, and then the exclamation sign, and then third. I'm going to close it. Let's go and click this at the bottom of the window again. So if you go to display, there's a lot of parameters that you can manipulate and change. But let's go to this display. Here you can see that there's comment type 1 and comment type 2. Let's change the color. You can change the color of the comment. Let's choose purple and okay. And here it is. It has changed it for you. Let's go back again. Display. And here's other parameters that you can play with. Obviously, you can play with the screen background color, the font you are going to use, the size. We'll keep it on the default size. Even you can change the plot option, the axis, the dimensions, the font. And these are just accessories of the software. Okay, let's just get more into thermodynamic stuff. So to begin with, I will show you a simple example. And here is it. So this example is a saturated R134A vapor at 40 Celsius is condensed at constant pressure to a saturated liquid in a closed piston cylinder system. Calculate the heat transfer and work done during this process. So let's start. As you can tell that at the first state, the phase of the R134A is vapor. So the quality will equal to 1, and the temperature is equal to 40 Celsius. At state 2, after it's condensed, with a constant pressure, it will become a saturated liquid. That means the quality is equal to 0. Let's go back to the software and write the givens. So T1 subscript 1 equal 40 Celsius. As you can see, I have written the unit inside parentheses, and that's where you're going to write the unit. Just let me quickly show you that. In the options, you're going to click to unit conversion info, and these are different dimensions this box will show you. And for every dimension, there's different units. So let's go to angles. So for example, you either can write the unit as radian or radians or just rad. It's obviously the same unit, just different way to write it or type it. Also, unit conversion formation. Here it shows you that if you want to just know the conversion between radius and degree, it will show you that every degree has that much of degree. Every radian has that much of degree, and every 1 degree has that much of radian. Obviously, it has for many dimensions. If you need just some information for you. And then let's go back to options. Here is some constants that's already stored in the software. For example, we have Planck's constant and its value with its unit. And let's see. We have the pi 3.142. There are many concepts for different, not only thermodynamics, but also for mathematics. We'll explore more in the options. Just let me type the example and solve it, and then I'll show you more. So as I said, it's a saturated vapor, so the quality equal subscript 1 equal to 1, and can write semicolon x subscript 2 equal to 0. So either you can write your variables in every line, or make to let the software differentiate between each equation. You have to put between them semicolon. Just let me change that. Instead of underscore, I will write inside the parentheses. Yeah. I'll show you why I will do it this way just in a minute. So now we have our givens, obviously constant pressure. Forget that about it. Now, to find the work and the heat transfer, the work equation is pressure, let's say, 1 times the specific volume at state 2 times, minus specific volume at state 1. Is the equation of the work done. So we need to find specific volume at state 2 and state 1. And for the specific or the heat transfer, in terms of specific enthalpy, H2 subtracted by H1. So we need to find the specific volume and the enthalpy for the two phases. To do that, we usually will go to the textbooks, find the tables of properties, and just by using the software, you'll save a lot of time. So let's go to options, function info. A window called function information will appear to you. As you can see here in the math and string function, different function will appear to you that's related to math. Then what we need is thermophysical properties. And there's also heat transfer, mechanical design, and other function for different fields. So let's go to thermophysical properties. So here in this box, you can choose the property that you need. So for our case, we need the specific volume. So it will be at the end since it's alphabetic. So we choose volume, and then we'll choose our substance, which is R134A. And here it is. And here we have independent properties. That means the property that's already given. And that says temperature and not pressure, but you can choose between pressure, specific internal energy, enthalpy, entropy. We have the quality since it's equal to 1, so we'll choose it. At this small box, you can change it. If we are working with subscript, as I was before, we can just underscore 1 or parenthesis 1. So it will change it for you. And then press past. And here we have our function to find the specific volume. Let's go to the second one to find the second specific volume. Again, options, function info. It's already chosen here. We don't have a second independent properties. Yeah, we don't have for the second base. But we know that pressure 1, pressure 2 are equal to other since it's a constant pressure process. So we can find P1 the same way. Go to function, pressure. We're going to choose pressure. We have the temperature, we have the quality, paste, and here it is, P1. And to find this volume again, we go function, volume, pressure, and then the quality, and let's change here to phase 2. Paste, and here we have it. We'll do the same for enthalpy. Let's choose enthalpy here. Enthalpy. No, here it is. Temperature, let's go to quality, change it to 1, and paste. As you can see, the way the function is written, first of all, you have the property, and then between the brackets, you have the name of the substance, and then the two independent properties. Usually, if you're using EES so much, you're going to easily memorize the way the function is written. So without going again to the option I choose, we're just going to copy and paste and then just change the numbers and the independent properties. So let's just say here we have x equal x2, and oh, it's already written here. You will write the pressure instead. So here we have it. We've solved the first example, but we are going, yes, first of all, before pressing and running the program to solve it for you, we're going to check the equation. So this equation has unmatched parentheses. Why is that? Oh, that's because I've written B in capital letter. So let's check it again. It has unmatched parentheses. Oh, sorry, that was a curly brackets. Now it's gonna be okay. So here it is. There are 11 equations, 11 variables. No errors were detected. Now I'm gonna check the unit. As you can see, we haven't actually input any unit except for the temperature one. That's why we have these errors. So here on the side of the window, you can enter your units. So for enthalpy will go kilojoule per kilogram, and pressure kilopascal. For the heat transfer, kilojoule per kilogram. And for a specific volume, m cubed, meter cubed per kilogram. And work done, kilojoule per kilogram. Please be aware that when you write a kilo, it should be a small letter, and when you write the joule, it should be a capital letter. So let's press check units again. No problem were detected. And then solve again. So when I, instead of writing as a subscript, I wrote that T1 and inside parentheses, I put 1. I wrote it in a way of an array. Just get that. Oh, right. So here we have our array table for state 1 and state 2. As you can see here, it says that four potential unit problems were detected. Check unit. We have these problems for these units. Let's go back and options, variable info. Here it's going to list for you the variable and the units, so you can by yourself check if you have entered the units. Obviously, the software sometimes I already entered in here, but the software sometimes get mixed up with the unit. I don't know why. So let's change it. Here you see. Just copy and paste it. The quality obviously has no unit. To apply and OK. Let's press solve again, and here it is. So we have the work and the heat transfer and a minus. So obviously there's a work in, since the work is in minus. So let's just change the subscript so it can give us a positive values. Now, with using EES, you can show you how. Now I'll show you how to use a parametric table to see how changing one variable affects another variables that you choose. So let's see how pressure will change. Let's see how work will change if pressure are changed. So you go to table, new parametric table, and choose the variable that you want to change. So let's P1 and add it, or you can double click and it will add. You can also remove it, add it. So here are the variables that you want. Let's just add, the heat transfer. So okay, and so to list the variables or list the numbers that you want to choose, you can click here. So here you can choose the number of rows. Let's make it 20. And let's just make the first value of the pressure is 100. Here you can enter the last value, the last row, or you can make it an increment. Just make an increment 100, so it will be in the first round, it will be 100, 200, 300, 400, or by multiply, let's say 2, it will goes as 100, 200, 400, 800, and every row will multiply by 2. Let's go to last linear and choose 1000 and press OK. Add 2 rows to apparently yes. And here it is. To run the program, you're going to press the button. So as you can see, an error has appeared. It says P1 is previously set to a value in the equation window. So to avoid that, let's make P1 a comment. Once again, and here it is. These are the values of the work and the heat transfer. As you can see, the work decreases with the increase of pressure and the heat transfer decreases with the increase of pressure. To plot, let's just plot these values in a diagram. So you go to plot, new plot window, XY plot. The x-axis, let's choose pressure, and the y-axis work. And here we can change the color of the line. Let's choose red, and the pattern of the line we can enter different symbols. Here you can choose the minimum and the maximum for the axis value for both the y and x-axis. Let's press OK, and here it is our diagram. Let's say you want to add the heat transfer values, but make it a secondary y-axis. So you can go overlay plot, overlay plot, press it, and the x-axis will be the same, y-axis Q. It's already changed for me the color and the symbol, so it won't get mixed, and press OK. Let's do that again. Oh, I haven't table 1 yet, that's correct. Plot 1. Oh, it should be, so this is the left axis. It should be work as before. And then you are going to choose the right y-axis, and then it will appear to you now. Just be sure to choose left or right axis. And you can do the same if you want another secondary x-axis. Click OK. Oops. Why does it work the same? Let's just modify it. Here you can modify and change the colors on the line or other things. So let's just delete this and delete this. And this is the one we inserted before. Okay. Go again, overlay plot, and choose the heat transfer, right Y scale. Press OK, and here it is. We have the work axis on the left, the Q and the heat transfer on the right. And here's your plot. If you right click, obviously you can modify it by not right click but double click, and you can change or go as before, plot and modify. So that's it for this example. Let's go for another example. Let me just close it. Open example 2. So for this one, I have already prepared the values for a refrigeration cycle that has 4 phases, 4 states. So for this example, we are going to plot the TS diagram and also the PV diagram if you want, if you have time, since we began late. Sorry about that. So you're going to check the unit again. I already did that before, and then no problem was detected. Let's just say solve it. So we have here the 4 states. First, the second, third, and fourth. To begin with the TS diagram, we're gonna go and choose plot, property plot. Here you can choose, if you have ideal gas, you're gonna choose from that, but we have a real fluid here. Since it's R134 the same. As you can see, let me just close it. I haven't written the name of the fluid here, And instead, since it's a lot of function that I've written here, I just wrote that R and the $ equal a single quotation inside, and then inside I wrote the name, just the substance that I'm using. So that's the fast way, or alternative way of writing the function if you are using the same fluid. So let's go back. Plots, property plot, and here you have it. In this box, you are going to choose your substance, which is R134A. And here's the type of different properties plots. We have the TS, TV, PV, PH, HS, TH. So we want the TS diagram. I would like to see this one. Let's make it here. Again, property plot. Here. Since we want to make the plot have the plot be corresponding to the points that we have chosen. As you can see here, you can choose the pressure lines and the volume lines, or let's change it to enthalpy lines. Since we already have corresponding to our points, we have 177 kilopascal. We will change that here, make it 177, and here we will change it to 1217. And this got back to enthalpy. There's no need to change it. These are the constant enthalpy, that the lines that will appear in the TS diagram. Let's just change the line, the color of the line. So it's blue, red, and I forgot to choose it again. R134A. Yeah, it is. So press OK. And here you have it, your diagram, TS diagram. If you want to make your state appears and numbered, you're gonna go again to plot, overlay plot, and here you're gonna be sure you have chosen the array table. That's the reason we always name the variables in array numbers, because it's more useful to us. So on the x-axis, we have the entropy, and the y-axis, the temperature. And here we go again. It's actually on the left scale. Now we're going to check this box, add point labels, subscript number. And yes, let's do it green. And let's choose this simple. And press OK. And here you have it. This is your TS diagram with your points on the diagram itself. As you can see, there's it is connected, but from 4 to 1 it's not connected. So if you just want to draw a line, you can do that. Here we go. Just press this line box, and you go from point 4, and again from 4 to 1. And here, if you press the ABC box, You can add the variable if you want, some variable, or just a text. So let's say TS plot, a TS plot, and let's change the color of it to purple, size, make it 18. Can change the font to Times New Roman, and then press OK. And here it is, your text. I believe that you can, where was it? Yes, for the parametric table, you can save it to your computer, and just by pressing here save, and even insert it again if you want. But obviously for the diagram you cannot. Well, obviously because the values are already in the table you are gonna save. But you can screenshot the diagram if you want. So let's go again and do the PV diagram. So property, PV, and for the temperature we have, let's do pH. Yeah, let's do pH. So for pH, we have these temperature that's corresponded to our temperatures. 160. Oh, let's do that. 320. 327. And 260. Oh, here should be 260. Since it's going from the smallest to the largest, it's increasing. So let's do 260 here. And here 320. So yes. And for the rest, no need for it. Let's just change the color so we can see it. And here's the pH. You can change, move the numbers so you can see clearly the lines. And yes, you can do different plots. Obviously, STV, PV, pH, HS. Where is our? Yeah, let's go back to our table. Modify plot. And here's our plot. It's just put the states and the numbers. Okay, choosing the pH diagram was a mistake. Let's choose. This obviously goes way back. Let's choose another property plot, PV. The temperatures as before. Close it so we can see the array table. Here we then choose the temperature. 260, 327.5. Here 320. And here 327. 0.5, and here's 2060. Oh, here's gonna be 320, and here 327.5. Change the colors. Or it's gonna be all black and you don't know which one is one. Go again to overlay plot, choose. First we have the P and the x-axis, x, h, and P in the y-axis. And we forgot to check this box. We'll do it again with another color. Don't forget to check this box, or instead there's no numbers will appear to you. And here we have it. And you can see your different state at the diagrams. That's it for the property plot. So in this software, there's different examples. You can, for animation, arrays, complex number. For animation, there's different examples that relate to thermodynamics. For example, change of phase of water in a piston cylinder. So click on it, now save. So here it appears to you an animation that you can change the pressure and the mass. And when you run it, it will shows you how the volume increases as the piston change or works or goes up. Yes, goes up. That's why the volume increases. Let's see different examples. Here we have the two-stroke internal combustion engine. Just scale it up a little more. And then let's start to play. And here it shows you different diagrams, T versus entropy, temperature versus data, pressure versus data, pressure versus volume. And I think this animation is already stored in the software, obviously for just for the education for students. So that's it for our workshop.